stuff. So we are going to have the second keynote of the conference. Tomorrow we will start at 8:30 with the Humming Fans keynote. So tomorrow should be easier. Everybody knows the drill, how to get here, everything, so no problem. So without further ado, I'm gonna ask Bob Miller to come in and introduce our keynote speaker.
Thanks, Juan. Well, formally, Whitney Newey is the Jane Berkowitz, Carlton, and Dennis William Carlton Professor of Economics at Massachusetts Institute of Technology. But really, Professor Newey doesn't need an introduction, because if I was to follow the lead by Professor Wu yesterday and asked, hands up everyone who's read something by Whitney Newey, I'd see a sea of hands. So that is a testimony, or would be a testimony to Whitney's impact on the profession. And in fact, I think that yesterday's lecture was an example of what he has brought over many years and is still bringing. He smiles, but yes, to us. The three features of the paper, the lecture that I just wanted to note today very briefly is, first of all, the depth with which he goes, like the Pacific Ocean. I'm swimming a few yards out. He is right out there past the continental shelf in terms of pulling in probability and statistics to us. So that is the sense in which those linkages across the statistical probability and economics literature is huge. That's the first thing, the depth. The second thing is the accessibility or the access he gives to us. Now, I didn't say yesterday's lecture was easy, but it is accessible. And the reason I say that is because I've seen other contributions that he's made that have then had impact. So that's the sense in which I think it's important. And the third feature of yesterday's lecture that is probably worth noting here is its relevance. In other words, it's not simply deep and accessible, but it's actually useful. And in this particular case, yesterday's lecture, what it was doing, at least from my perspective, was saying, well, here is a way of dealing with vectors in your state space and not interpolating to make them a finite set, which Whitney had already done, I think, more or less as a graduate student or soon after, when you did the two-stage GMM stuff. You know, when you've got a finite number, you put them together with one set of parameters and both sets of parameters, CCPs up here and the other, everything down there. But saying, okay, let's not interpolate anymore. In other words, let's take the data as it is and work with it and incorporate that into the confidence intervals, into the precision, not to mention the asymptotic bias that you would get if you didn't follow a procedure like that. So those are the three features which I think, to some extent, or three other features, that would be a better way of putting it, that explain why Professor Newey stands where he does as a leader in the microeconometrics field today, unquestionably. It's your fault, Whitney.
Well, that was really kind. And I always follow the advice I once heard that's really good, which is don't inhale. Um, so I really appreciate that. And so if you liked yesterday's lecture, hopefully you'll like this talk as well. It's going to be basically the conditional version of that, and I'm going to talk about that. Okay, so conditional influence functions. First of all, this is joint with Victor Cherzukov and Basilis Phaganis. And there's the archive post from last year, and it's being under revision right now. So this is a conditional version of what we talked about, basically. Okay, and so the interesting thing about this is there wasn't a conditional version of influence function before this paper, as far as I know. Although there were a number of interesting people who had used the ideas here that are here. So we kind of extended and generalized some of those ideas. Okay, so there's many non-parametric conditional objects of interest, right? We've all done that if we've done anything non-parametric. Conditional meaning, right? Conditional on some variable like income. We want to know how some outcome varies with income on average. Okay, and another example is actually the conditional average treatment effect, conditional on one or more key covariates. So we're not going to try and condition on all the covariates. We're going to look at the average treatment effect conditional on a couple, one maybe covariate. Okay, so that's an example, something that's interesting. Pointer, right? So, right, conditional on one or more key covariates. An economic example is average welfare effects of increasing price of a good. You know, the average equivalent variation conditional on income. We'd like to know how taxes might affect the average welfare of individuals, conditional on income. That's a good thing to do in application. And also, you can think about this as a way to try and provide some kind of low-dimensional summaries of high-dimensional objects. And certainly for the average treatment effect, those can be high-dimensional objects if you have a lot of covariates. Okay, so what we give in the paper is influence functions for conditional objects of interest. And these, okay, so I'll get to explaining the background of the statistics literature. The influence function isn't a conditional object. But we're going to extend that idea to conditional objects of interest, and that actually does some useful things. Similarly to the classic influence function of a function of a cumulative CDF, that's what the influence function is about. It's a function of CDF, functional of the CDF. Conditional influence functions can be used to construct name and orthogonal estimating equations for conditional non-parametric objects. Okay. And that's so machine learning can be used as to estimate functions on which the objects depend. Most notably, conditional choice probabilities can be used to estimate conditional objects, right? For example. And so that's one of the things that can be done with conditional influence functions is you can get name and orthogonal estimating equations. Okay? Another thing is you can quantify local effects of this misspecification on conditional objects, right? So there's this nice paper like by Andrews, Jenskow, and Shapiro published in the PJE where they look at the effect of misspecification on structural models, things that are of interest in structural models. And you can do that for conditional objects as well now using this approach. And then also you can look at conditional local policy effects. We're still thinking about that. The referee said you need to motivate this better. So we're going to do that. And I actually think I have an idea about something that might be interesting to look at actually from things that Bob said yesterday. So here we're going to mostly focus in this talk on constructing name and orthogonal estimating equations, but also touch on other uses for the conditional influence function. Okay. So estimators of objects of interest, conditional objects of interest based on machine learners have previously appeared in the literature. Convergence rates for conditional objects were given in a Foster and Stroganos paper in the Annals of Statistics. Whitney Newey actually gave an estimator of average potential outcome for continuous treatment, where she explicitly used and cited influence function. Okay, so you know, what she did is actually, you can formalize it, and you can think of, we can do that for her estimator of the average potential outcome conditional on what that is, average potential outcome conditional on a particular value of treatment. That's what she derived, and she talked about how to estimate it and created an orthogonal moment function. Actually, turns out if you do it the right way, it's can be explained in terms of conditional influence function. So that's the point is, you know, some of these things, there are already existing examples of that. Okay. Another nice one is linear projection estimator in a paper by Semenova and Chernozukov. Here is Semenova, the student from MIT who is a Berkeley. Okay. And then kernel regression with kernel regression estimators with automatic debiasing, and this paper with Victor and Google saying that was published in the Econometrics. Okay, so that's also a conditional object. But we didn't say anything about conditional influence functions, but it turned out they can exist, and they do exist in each of these cases. Okay, and you can use that setting to go beyond these things. All of these were kind of developed just to figure out how to estimate particular objects, but they're all special cases of conditional influence function, and then you can use that idea or that object to create orthogonal moment functions in settings beyond these. Okay, so that's the usefulness of it. Not just a generalization that includes everything, but it you know, gives you a structure that you can then use to apply to other things besides the. There's more people who have done this. Estimators of the conditional average treatment effect in Kennedy et al. Paper published in the Annals a year or so ago. Annals of Statistics. That was really not what we're doing. That was about the conditional average treatment effect conditions on all the covariates. And so they did some careful analysis of that. And that's great, but that's not what we're doing. We're going to look at conditional average treatment effects conditional on a few covariates, like one, say income. Okay. There's also some efficiency calculations given in Lutka and Chung. This involves, they were looking at well, never mind. I'm just going to leave it at that. Okay. Some other estimators that when, you know, this paper was posted on arXiv, it was, you know, at the end of the year, it was posted on a holiday, and I got emails the next day saying, look at these papers. So they'll be included in the references in the revised version. Okay. What we do here is we just talk about what a conditional influence function is. It turns out it exists, which people didn't really know about before, and I'll get to the reasons for that later, and then show how it can be used to construct name and orthogonal conditional moment functions for estimating conditional objects of interest. And so then the point of all this is this provides a general way of constructing name and orthogonal moment functions rather than that are conditional ones. Okay, conditional ones rather than having to guess their form in each particular case of a conditional object for interest event. Okay. Okay, so what do we do? A number of people have done these related things before. What do? We give conditional influence functions. And then we show how they can be used to construct name and orthogonal estimating equations, and then briefly discuss the other possible uses. And describe the estimators based on name and orthogonality. Okay. So that's what we're doing. Okay, conditional influence function. What is that? Well, let me first talk a little bit about what the influence function is. And again, you know, for those of you who were there at the the winter school talk yesterday, this will look familiar. Okay, so recall the classic influence function. So this is what an influence function is, dating to Campbell and before that to back to a long time before 1947, right? So take the same notation as yesterday. W is a data observation. F is a CDF of one observation, which has true value x0, and theta of F is some parameter of interest, a function of the data distribution. Of course, okay, we'll get to examples of that in a little bit. Okay, and then we take this. We start at the true distribution and we take a little bit of some other distribution, take a convex combination of the true distribution and some other distribution. And this is going to be allowed to be unrestricted in what we're doing. This H represents local variation. You can think about it as F naught plus epsilon times H minus F naught. So that's an H minus F naught is kind of the deviation of this distribution away from the truth. Epsilon times H minus F. Okay, the influence function, when it exists, is this function, which we're now going to call C, satisfying the integral. I'm sorry, you take the derivative of the object you're interested in with respect to epsilon. That's a scalar, right? This is just a scalar derivative. The influence function is such that whatever H is, you can represent this derivative as the expectation of this function, this influence function, when H is the true derivative. And that's what that object means. It's the integral over this distribution of phi of W. Okay? And we normalize so that it has mean 0. Okay? And so this is sometimes called the co-derivative of theta of F at F0. Okay. So what's the conditional influence function? It's that for the conditional distribution, for a conditional distribution. Okay, so so the notation we're going to use is a little awkward mathematically, but it works for the calculations. We're going to actually talk about, conditioning on a particular value of a random variable. It's not really what it is, but that's for our purposes, that's fine. Okay, and it works for the calculations. So take F of B, take that to be the CDF of one observation conditioned on some random variable B equal to little b. Okay, so particular value of the conditioning variable, we're going to use that. It has, and that true CDF again, true conditional CDF at B is going to be F of 0 at superscript B. Theta of F of B is going to be a parameter of interest, right? Having a true value of theta 0 of B is the parameter evaluated at F. Okay. And then we're going to take a deviation in this away from the true conditional distribution. Okay, F of epsilon of B is 1 minus epsilon F0 of B plus epsilon H of B for alternative CDF H of B. Okay, the conditional influence function, when it exists, is the function psi 0 of B is going to depend on B, right? It's going to depend on the value you're conditioning on, satisfying. Again, it's the derivative with respect to the epsilon, and it's the characterizing a deviation of the distribution away from the truth, F0, right, is the integral over the conditional distribution, H of B, of psi 0 V of W. And it has conditional expectation 0 for that distribution. The conditional expectation of this is at V equals V, I should have there, is equal to 0. Okay, so those sometimes exist. Okay, now there's a couple of components that are not completely obvious here. One is, this thing has to be a functional of the conditional distribution conditioned on v equals little v. Okay, so it's got to be something that you can write as a functional of the conditional distribution. Turns out the conditional mean is like that. Okay, why? Well, it turns out, right, that we know this, like the conditional mean minimizes the expected squared error of the difference of y and any function of x. That's the conditional mean. It minimizes an unconditional. It minimizes an unconditional. The expected squared deviation of y and any function of x. Okay, the conditional mean of y given x minimizes that. Okay. Well, that's true for anything you condition on that's an x too. It always minimizes the conditional mean of the expectation of y minus the conditional object squared, right? Conditioned on the conditional expectation, and that's true whatever you condition on. You can show that, right? I mean, if it minimizes the unconditional, then it's going to minimize any conditional thing too. Anyway, I don't really go into that, but okay. So there are examples of this, but it's not exactly obvious. Okay, that you can write the thing you're interested in as this, but you can, and you can do it for conditional means. And I'll come back to this later because you can't do it, to the best of my knowledge, for some other things. Okay, like projections, least squares projections on a set of functions. And those don't really have a conditional formulation, as far as I know. Okay. So let's look at a running example. We'll just do one example for exposition purposes. Conditional average potential outcome. Something that we're all familiar with from causal analysis. There's an outcome variable y. It's the outcome under treatment when treated. The d is the treatment dummy variable, right? So that's our outcome variable. Conditional expectation of I'm sorry, y, the outcome is the outcome under treatment times the treatment dummy plus the outcome under a non-treatment times 1 minus the treatment dummy, the usual formulation of that. Okay, y1 and y0 are potential outcomes with and without treatment, and we'll make the assumption that they are mean independent of treatment, conditional on covariance C, and that the propensity score, the probability of treatment conditioned on Z is greater than 0 with probability 1. Okay, so we're only going to look at the average potential outcome conditioned on treatment, so we only need the greater than 0 for identification. Okay, so let's let V be some function in the covariance, for example, like a single covariance. Okay, and then let X be the things we're going to condition on in the regression, the treatment variable and Z, right? So W is going to here consist of Y and X. That's one observation, it's Y and X. And the gamma naught we're going to look at is the expectation of Y given X. Okay? An object of interest is the average potential outcome conditioned on this variable V. Okay? And we know from the work on average treatment effects that, that is equal to the expectation of gamma 0 evaluated at the conditional mean evaluated at the treatment equal 1. In other words, for the treated, okay, conditioned on V. Okay, we know that from causal analysis. Okay, that has a conditional influence function. And what is it? It's this gamma 0, the conditional mean evaluated at 1 and Z, minus theta naught of V, the object of interest, and then plus an alpha naught times y minus gamma naught. And notice, that looks like the thing that showed up for an unconditional influence function. Turns out it same thing shows up in the conditional influence function. Okay, and the alpha naught is the same thing as you get in the regular influence function is D, the treatment indicator divided by propensity score. Okay, so that's what that conditional influence function turns out to be in for the average potential outcome for the treated. Okay, so now these conditional influence functions, as I said in the introduction, can be used to construct name and orthogonal estimating equation for a conditional non-parametric object of interest where the unknown functions have zero first order effect on the conditional objects of interest, and also be used to, this again from the introduction, quantify local effects of the specification on the conditional object and be used to define conditional local policy effect. Yeah, the thing is, the reason nobody ever thought about this in statistics, as far as we know, is that it can't be used to characterize asymptotic variances. Okay, so that's what, you know, you often heard the term efficient influence function. Right, and that refers to, you know, the efficient way to estimate something and what it's, you know, an estimator, it has its asymptotic equivalent to a sample average of the efficient influence function, and it's an efficient estimate. Okay, you can't do that here. That's why nobody probably even thought of doing this. At least probably somebody probably thought of this. That's not interesting because it doesn't characterize asymptotic variance. It doesn't give you sort of efficiency calculations, and that's because it's non-parametric. Things that cannot be used to characterize asymptotic variances or make efficiency comparisons for conditional parameters. Why? Because they're non-parametric. And so we don't know what's the general efficient way to estimate a conditional mean. We don't know that, actually. We don't know really the constant. And what's going on is there's different ways of localizing. And so, you know, you can do kernel regression, you can do local linear regression, you can do series regression. They all have different asymptotic variances, even though they're estimating the same object non-parametrically. Okay, so that's the thing that apparently it can't be used for. And we don't have we haven't been trying to do a general theory of efficiency or even paying attention to that for non-parametric things, right? So that's probably why, you know, people haven't thought about this before. We just want to use them for creating name and orthogonal moment functions. That you can do. Okay, so that you can do. Okay. Because we're kind of into this debiased machine learning. If it's useful in applications, you know, that you can use. Okay. All right, so that's so you can use it to do these things, but not for that. Okay. So anyway, okay. So name and orthogonal estimating equations. Well, if you were here yesterday, you know, this will look familiar. Okay. These are conditional estimating equations for objects of interest where the first order effect of the nuisance functions on the conditional estimating equation is zero. And we're going to start in the same way we started yesterday with an identifying conditional moment function. Okay. So let's let gamma denote a first step function that helps identify theta naught of V. In the running example, that was expectation of y given x, where x is treatment, the treatment dummy, and the covariance. Let g of w gamma theta be a function of a data observation, gamma and theta. So what that represents is theta is a possible theta of B, right? So theta really depends on B. This is going to be a possible conditional value of the conditional object. Assume that theta B solves this conditional moment restriction. Okay, so that's our starting point, is a conditional moment restriction now rather than an unconditional one before. And in the running example, G is just, gamma evaluated the conditional mean, possible conditional mean function, evaluated the treatment, the treatment from equal 1, minus the theta of the thing that you're trying to identify. Okay, so again, we take the conditional expectation here, right, of this evaluated at the true regression, and you solve for theta of B, and you get our average potential outcome conditioned on treatment. Okay, so that's the running example. Okay, we construct name and orthogonal moment functions by adding to that identifying moment function exactly the conditional analog of what we did yesterday. So you take the expectation of the moment function, you evaluated it in any theta, and you evaluated it in any theta, we conditioned on B, okay, that B is equal to B. And we're going to take the derivative of that with respect to the epsilon, which is inside f of B. And a conditional influence function is something that satisfies that this, it's just the conditional influence function we previously defined for this object. The expectation of G, the moment function, okay, evaluated at gamma as the distribution of the conditional distribution given B varies away from the truth. Okay, and that's what a conditional influence function is. It satisfies that conditional equality that we had before, that the derivative with respect to the epsilon is the integral of over the conditional distribution of the data, right, of this object. Okay, so then the conditional name and orthogonal moment equation is just G plus B, phi, psi, phi, right? Okay, and in the running example, the phi is just alpha times y minus gamma of x. So that the name and orthogonal, conditional orthogonal moment equation is gamma 1 z minus theta b plus alpha x, y minus gamma x. Okay, and again, alpha naught is the ratio of the treatment indicator to the propensity score. Okay, so that's how you construct a conditional name and orthogonal estimating equation. Same way as before, except with the conditional distribution. Okay. And that's the thing that wasn't known to the best of our knowledge. Okay. That this worked quite generally. Okay. So it has two orthogonality properties. They're exactly the ones that we had before, only the conditional version. Okay. All right, so this is this wasn't on the slide yesterday, but this is kind of the orthogonality property that corresponds to the definition, which is that as you vary gamma with epsilon varying inside f, that derivative is 0 of the conditional expectation of the orthogonal moment condition. And then the other one is like what we had before, the expectation of C, W, gamma naught, and alpha, the conditional expectation condition on V is equal to 0 for all alpha. So actually, as alpha moves around, you get global robustness, whatever this alpha is. Now that requires something, and I'll get to that in a minute. We said this before, but we'll put up the equation this time. Property 1 follows from differentiating with respect to epsilon, the mean 0 property of this It's y-direction term speed. Okay, if you just, I mean, it's just to differentiate, use the chain rule, right? This epsilon appears two places. Here, differentiate, right? This with respect to epsilon, you get the sum of the derivative partial root in the two places. That has to equal to 0. That's actually just that equation. We can show that it's that equation. Okay. Property 2, I'm gonna talk about how much time have I got actually? What do I am? Almost done. Property 2 is kind of, I'm going to talk about what that is because it's kind of interesting. Okay. Property 2 depends on there being some f of v out there, such that whatever alpha you're taking the expectation, whatever alpha you're evaluating in here in that expectation can be represented as an alpha for f of v, and that gamma can be set equal to the truth. So there's some distribution where alpha changes to be what you want and what you look at, and gamma doesn't. And that's true quite generally. This is gamma is a conditional mean given x. The alpha, look at what it only depends in the example. If you look at alpha, it only depends on where is it? Oops, going the wrong way. Right, it only depends on the regressor. So, you know, you can change the distribution of the regressor, right? So that you get whatever you want here. Okay. And at least for alpha, that's not negative, I guess. Okay, and so, okay, so you plug in that alpha here, and then if you look at this thing, if you look at that, this looks like the formula for the derivative, only we swap. This is the truth here, and in the formula, this is 8. Okay. So the way you get this to show this is true is you just put in a deviation where you started at b and then you go back towards the true distribution. Okay, and then when you differentiate, it turns out you're just differentiating this to get this, and the derivative of this with respect to epsilon is 0 because gamma is not varying. Okay, so that's the way you get that result. Okay, so the point of what is that result? It's global robustness in this extra function that you have to estimate. Okay, it's global robustness of the orthogonal moment function in this extra thing that shows up to be by it. Okay. Okay, so in the regularity conditions, we got this is now the derivative condition we had yesterday for gamma, only conditional in v, and so that's the sense in which you have an orthogonality with respect to gamma. It has 0 first order effect on the conditional mean, and also 2, you know, 2 implies that there's a global property of orthogonal moment function that whatever alpha you put in, it has mean 0 conditional on v. Okay, so more than you wanted to know, but it turns out to be useful for estimating, you know, for doing Neyman orthogonal conditional estimating. Okay. What? How much?
About 15. Some 15 minutes.
Okay, 15 minutes. Okay, great. That's fine. Okay. Okay. So in the running example, this is the Neyman orthogonal conditional moment, right? The estimating equation, as it were, conditional moment condition. And if you actually look at, plug in any gamma and alpha, look at the expectation of this, I won't go through the algebra, but it's quadratic in alpha and gamma, and so that means it's small order, right? And these, that either of these, the difference of these from their truth, and so, and it has the doubly robust form that if either alpha is equal to alpha naught or gamma is equal to gamma naught, then you get 0. or the, you get 0 at the true parameter value here. Okay, so it's doubly robust, conditionally. Other uses of conditional influence functions, I'm gonna skip those, okay, we don't really have much to say. The policy thing would be interesting to do, we haven't really done much with that. Johnstown and Shapiro, it's kind of you can do what they did. They just use the influence function as a measure of the effect of shifting the distribution away from the truth on the parameter of interest. Okay, that's what they sort of motivated a different way, but it's the same thing. It's the influence function, and you can do that for the conditional, using the conditional influence function for the object here, for the conditional object here. Okay, so that example generalizes to any functional of conditional mean, okay, with certain properties. Okay, so you can generalize that example to any functional of conditional mean that has this form: expectation of m of w gamma naught b, and that's the object of interest for some m. Okay, gamma naught is the conditional mean, b is some function of the conditioning variable. Right, and this is the running example. M of w is just gamma 1 and z, and x is b and z. The key condition that for the conditional influence function to exist is that there's alpha naught such that you have a conditional representation. Okay, so it's a conditional version of the kind of representation condition you have in the end that we have, for a long time. Under that condition, then you get a similar result to what we did for the example. Okay, when there's a conditional representation, then the orthogonal moment function is what you would expect. Let's skip this. It's that. It's m minus theta naught of v plus alpha naught with gamma minus gamma naught. And it turns out that this representation, this conditional representation holds for exactly the same alpha naught that you use for the unconditional case. I don't know. I mean, sure, there's a good mathematical reason for that. I don't know what it is exactly, but anyway. What we were using before in the unconditional case, what we're using before in the unconditional case turns out it works conditionally too. You put in whatever the function is m, you look at the conditional version of that parameter, right? It turns out that the alpha naught before, for the unconditional case, is actually works conditionally. And it doesn't work in every case. What's going on here is this object has to be some interesting thing where you're integrating out over something that gets you a representation. And so in the case of the average potential outcome, you can't do this with D. You don't have this with D, the treatment variable. You can get a conditional average potential outcome, name an orthogonal estimating equation for that, as long as you're conditioning on some function of the covariance, not if you're conditioning on the treatment. That makes perfect sense. You're already conditioning on it anyway in the object we're interested in. So anyway. So, and that sort of that's the math behind this. Actually, you're conditioning on the covariance here for the in that example here. Okay. All right. Okay, you can generalize this. Doesn't work just for the conditional mean. Anything which minimizes some objective functions. So conditional quantiles you can do this for. Okay, functions of conditional quantiles you can get conditional influence functions for, and then construct name and orthogonal estimating equation. Okay, so what do we do with that? Well, what we do with that is, the way you can then use this name of orthogonal estimating equation to estimate the parameters of interest is just simply to add this bias correction. Okay, so it's kind of like we did before. We're going to add the bias correction. We take object of interest, conditional mean of this at the true gamma naught is the parameter we're interested in. Okay, we add the bias correction. Okay, so we create this pseudo. You can think of it as a pseudo outcome. It's the object where, the object to whose conditional expectation is what we're interested in. Yeah, that's what we're looking at. The conditional expectation is what we're interested in, and then you add the bias correction to that. And then run a non-parametric regression of S hat I on DI to estimate the object you're interested in. Okay. We do use cross-fitting again, like we talked about yesterday. So you do cross-fitting where you do this thing where you estimate the alpha hat and the gamma hat from other observations, and then you do the non-parametric estimation over groups of data, run a non-parametric regression of SIL on DI at V to estimate data not at V. Right. So what non-parametric regression do you do? Well, for partial linear is really good. We know it's really good. So we in the paper we analyze partial linear regression. Okay. Okay. Here, just for expositional purposes, we consider a kernel regression estimator just to give an explicit formula. Let K of U be a PDF, H is the bandwidth, and R the dimension of V. Okay. And then this is just a standard kernel regression formula where what we've done is it's kernel regression where we have, used this pseudo outcome here as the thing we're taking a conditional mean of. Okay. And you can just do this, and that's fine. Okay. In practice, I'm going to say that a local linear regression is preferable, and that's what we analyze in the paper. We do the asymptotics for that, okay, and give conditions under which the asymptotic variance of this non-parametric estimator is the same as if you plugged in the true values of the gamma, and you plugged in the true gamma naught and the true alpha. Okay. And we give conditions for that for local linear regression. Here they are. Okay. I give the bandwidth conditions for this is true for kernel regression too, but also true for local linear regression. Straightforward to give conditions for this estimator to have the same limiting distribution as the estimator where S hat is replaced by SI. In other words, where the estimation of gamma and alpha doesn't affect the asymptotic variance. For a bounded kernel, okay, so that's critical actually, because we're gonna, I'll get to that in just a second. To say, well, for a bounded kernel, including local linear regression, a key condition is that this is the key rate conditions that we use to get the result that the estimation of gamma and alpha doesn't matter. Is that the mean squared error approximating, gamma hat by gamma naught. So this is a population mean squared error. That's what this is. That's what this says. This norm of A thing is just the squared, the L2 norm on a random variable. And under this condition, you need this to go now. Before, okay, I'll get back to that. You need this to go to 0 faster than the bandwidth raised to the R/2. Same thing for alpha hat, and then you need a product rate condition. The product of the the approximation error and gamma hat and alpha hat times root n has to also go to 0 faster than h to the R/2. So that's a stronger condition than the non-parametric case. I'm sorry, yeah, than than an unconditional case. That's a stronger condition. And that you can put in one here, you can put in one here, and you can put in one here. And what's happening here is you have to do, not you have to, but we use this h to the r over 2 because you have an h in the denominator of the kernel, and you have to get rid of that. Okay, you have to deal with it somehow. So that's a strong condition, and stronger than you need for an unconditional. Okay. All right. But the cool thing about this is these are not non-parametric rates, they're just L2 rates. And so that's actually very important for machine learners, because for many machine learners, this is all we know is an L2 rate condition. Okay, so to get this to apply to like neural nets, it's super useful to have this. Okay, all we know is L2 rates for neural nets. We don't know anything about uniform convergence or fourth order convergence. We just know what's available in the literature or mean squared error rates for neural nets. And the same thing now pretty recently for random forest. Okay, so to get, it's really nice, and it makes these things applicable to neural net estimators of a regression and a neural net estimator of this. Okay, on the alpha, and so that's the nice feature of this. And it is true, if you strengthen the L2 rates to L4 rates, fourth moment here instead of second moment, then you can weaken H conditions. Okay, but the thing is, that doesn't apply to neural nets. So this is the best we've got at the moment. We don't know whether it's the best you can do. The key thing, we just use the kernel bounded and kind of then throw out soup over the kernel. And kernel bounded by, the division of the bandwidth that you have in the kernel regression, right? So this gets rid of the bandwidth term. It's h to the r. It's the reason it's h to the r over 2 is because the convergence rate is slower. So that because it's slower, there's an h which shows up in the convergence, h to the r which shows up in the right, and so that cancels h to the r over 2 that shows up in the right. So that cancels one of these h to the r's in the denominator, and that's why you get that condition. More than you wanted to know about the asymptotic. Okay. But the nice feature of it is, you just have mean square conditions here, and there, which, we don't be satisfied under certain restrictions on the regression for neural net. Okay, what else? Alpha, still gotta get alpha. Well, as we said, for the conditional mean, it's the same alpha. In all the examples we know of at least, and so you just use the same method to get it. Okay, so this is the automatic estimator of alpha. Okay, for conditional mean when you're estimating the conditional expectation of this. Actually, when you're estimating the expectation of this in the unconditional. Okay. Okay, so just like your neural nets here, if you want, with set of A of approximating functions with a possible penalty added, which isn't there, and just do this over neural nets, and that gives you neural net estimator, and references to that. Okay, so that's conditional influence functions. You can use them to estimate conditional objects of interest for when the object of interest depends on the conditional mean. You can estimate them in such a way that the estimation of alpha, of gamma and alpha, don't affect the asymptotic variance. Okay, so we've given conditional influence function. We showed how to construct conditionally named and orthogonal moment functions. We've touched on other uses, and for the referee's sake, we've got to do some more of that. And suggestions are welcome. And we've described devised machine learning and conditional non-parametric parameters and have given some rate conditions. That's conditional influence functions and what that's about. Any questions? Yes.
Yeah, to ask how much extra work did you do? I want to extend your framework to the case where both treatment and the conditional variable they are both continuous.
You can do that, and in fact, Whitney Newey has already kind of done that. Yeah, so what she was estimating was the average potential out for a continuous treatment variable. And so for that, you're actually conditioning. Yeah, you can extend it. Yeah.
Here it was the potential because this both of them has the structure.
She did actually. Yeah, and some of the earlier papers have used that too, actually, so including our paper about, kernel regression things. So, yeah.
Second question, sir.
Sure.
Is a
fine.
condition when there's a difficulty of characterizing the variance. Do you think for a particular non-conventional labels or for general
For general like that, it depends on how you localize. You can localize with kernels, which is kind of a one-time localization. You can do it with series. You can do a local linear regression. It depends on how you localize. The asymptotic variance depends on that, and so it's kind of like that's all about with non-parametric estimation. To get rid of the bias, you have to use observations that are arbitrarily close to the point you're conditioning on, right? Otherwise, there's some bias from the function not being the right value. And so, it's not clear what the that there is an optimal way to do that. You just do it different ways. Case by case, and each different case, not well known, but there are formulas. There are actually post-form formulas for the asymptotic variance of the series estimate. And my work in Xiao Hong sort of ignore that and just go straight for the standard error, right? There are some post formulas that are different than the kernel formula, and that's different from the local linear formula. So, that's just, we don't have a theory for what the optimal constant is for non-parametric regression. That's kind of what you're getting with that, with semi-parametric efficiency, is you're getting, what's the best asymptotic, what's the lowest asymptotic variance. That's kind of like getting a constant, right, in the limit, right, in the mean squared error is ordered. And we don't know that for unconditional, for conditional means, we don't know that.
Thank you very much.
Any other questions?
Okay, there is no other questions. Now a round of applause.